Today I want to talk a little bit about the energy of ionic bonds, because when we first teach you about ionic bonding, we say, well, there's a cation and an anion. So let's take magnesium, for example, which likes to form a 2+ ion, and bromide, which is a -1 ion. And we'd say if we were going to pair these together, then the charges have to balance out, right? That's what we teach you. So I have to have the right ratio of elements in order to have a net neutral charge for your ionic compound. So we would say, well, I need 2 bromides for every 1 magnesium, and that would be my chemical formula. Well, why is that? If we relate this to our Lewis dot structures, if we look at magnesium, which is one of our alkaline earth metals, so it's in column 2A or 2, so it has 2 valence electrons, and we have bromine in their neutral state. I have 2 bromines that are halogens, so that would be in column 17 or 7A, which means they have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So what's going on in this is a transfer of electrons, and that's what causes ions to form, is a transfer of electrons. They can't just be lost. We talk about losing electrons, but it's not like, I lost them, I can't find them. It's, I am transferring them to something else, and then the resulting charges from that form electrostatic attraction. So my magnesium here is going to give one of these electrons to my bromine, making it have a full octet, right? Because we know that elements like to try to have a full valence. For most, that's 8 electrons. So that's one way for it to do it. But then magnesium would still have that 1 electron left over. So we need another bromine here with its 7 valence electrons to snag that other one. So if we're thinking about this from a Lewis dot structure standpoint, then this transfer of electrons gives this net +2 charge. Now magnesium's happy because it has a full lower level, right? So if we think about magnesium 2+, it's isoelectronic with neon, right? So here's my magnesium. I lose 2 electrons. Now I'm happy at neon, so it's got a full second shell, if we're thinking about it in terms of the Bohr model of the atom. And my bromides have a full octet as well, so they would look like krypton if we're thinking about things that they're isoelectronic with. So krypton is here. When I gain that 1 electron, then I'd be there at the end of my 4th period. Okay, so we have our cation and our anion and this electrostatic attraction between them that comes because of this transfer of electrons. But this transfer of electrons takes energy. This electron just isn't going to magically move. I mean, we've talked about quantum mechanics, so some of it feels like magic. I understand that, but it takes energy for this process to occur. It takes energy to move these electrons around. And these bromides are going to release energy when they have a full valence, because that's a favorable thing. So the energy that it takes to remove an electron is called the ionization energy. And you can have multiple levels. So the ionization energy is the energy that it takes to remove 1 electron. But we can have a first ionization energy, that's that first electron. We can have a second ionization energy, that would be to remove the first 2, third ionization energy, etc. And ionization energy, if we're thinking about our periodic table, and here's a little rough schematic of it. If we're thinking about periodic trends, then ionization energy tends to increase kind of going across the periodic table. It's harder to rip electrons away from things if they have full shells. It's easier to do it if they have fewer electrons. So there's kind of a couple different peaks here, but in general, it takes more energy to remove them the further you get to the right-hand side of the periodic table. Now, it's energetically favorable to have a full valence. That's what the octet rule really says, is that things like to have a full valence because it's energetically favorable to have these full shells, to have all of the electrons in the orbitals for that particular shell, than it is to have some just hanging out here like this bromide has, or the bromine, before it becomes bromide, just has this individual electron here. So there's energy that's released when we gain electrons. And this is called, this is related to what is called the electron affinity. So electron affinity is really how much things want to, how hard it is really, let's put it that way, how hard it is to pull an electron away from something that has already gotten one. So if I was to have my bromide ion, then I'd have to put in some pretty serious amount of energy in order to rip that one back away from it. So the energy that I get that's going to be released when I gain it is going to be the negative electron affinity. So let's put a little definition there. That's the energy that is released when electron is gained. And again, I'm kind of throwing around terms like gaining and losing without an energetic component to it, but it is really energy is going in to rip away these electrons. Then the energy is released once we have these in a lower state. It's a happier state. It's a more favorable energetic state. So there's kind of this balance between the two. And if I wanted to figure out what the energy of this process is, then I'd have to find out the ionization energy that it took to make magnesium, magnesium 2+, and the ionization energy that it took to take, or the negative electron affinity, so the opposite then, that it took to form those two bromide ions. So let's look at those numbers just for sake of argument, because we're scientists, and so we like to look at the numbers. So my first ionization energy, so this is for magnesium, because we're saying how much energy does it take for me to rip away electrons from magnesium in its ground state. So the first ionization energy is equal to 738 kilojoules per mole. So for every 1 mole of magnesium, it takes 738 kilojoules to rip away that first electron on each of them. Now the second ionization energy, to take away that second one, is 1,451 kilojoules per mole. And this is kind of an important feature here. The second ionization energy is always going to be greater than the first. It always takes a lot more energy to rip away that second electron than the first one. So you're always going to see a pretty marked improvement, or not improvement, but increase, I guess. Could be an improvement, I guess. But a marked increase in the energy that is required to remove that second electron compared to the first. So that means total, in order to go from magnesium to magnesium 2+, from an energy standpoint, and this kind of looks like a half reaction in redox, right? So we could kind of think about this as a plus 2 electrons because the electrons are lost, so this is being oxidized. Then my delta H for this process is going to be the sum of these two, right? And I can do that because of things like Hess's law. 9 kilojoules per mole. That says that I can take the sum of things. This is a state function. It's not a path function. It's path independent. So I can add together the steps that it took to get there. So this is a lot of energy. I had to put a lot of energy in. It's an endothermic process, which makes sense because I have to put energy in to rip those electrons away. And now if we're comparing that to the energy that we get out from our bromides, so we'd talk about 2 bromines going to 2 bromides. And again, if we're thinking about this like half reactions, then I'd be adding 2 electrons to the reactant side to make that possible because it's a reduction. Then I'd need to look up the electron affinity for this. And so the electron affinity for 1 bromine is negative, so for 1 electron affinity. And again, electron affinity is the amount of energy that it takes to rip away an electron once the electron has already been added. So once it's a negative anion, then how much energy do I have to take to rip that electron back away? How much does it want to hold on to that gained electron? So the opposite of that is how much is released when that electron forms in the first place, or when it creates the anion in the first place. Okay, so the electron affinity for bromine is negative 325 kilojoules per mole. Makes sense that it's negative because we're talking about this release, and again this is the negative electron affinity, so that's already factored in. So the delta H for this process is going to be 2 times that, right? Because we have 2 of my bromines here, 2 moles of my bromines becoming 2 moles of bromides. So we end up with negative 650 kilojoules per mole. Okay, now what all this is setting up is really looking at the energy of the process, because there is energy associated with every single step along the way. So every time we gain and lose electrons, there's an energy, there's a process associated with it. And one of the things that we can measure about this is the attraction between these ions once they form. Because if we're going back to our kind of magnesium and bromide there, what we said at the beginning and what we always talk about when we're first introducing ionic bonding to chemistry students is, well, there's opposites attract, right? So I have a negative thing and a positive thing, and just like 2 opposite ends of a magnet, they're going to attract together. Well, I can measure the force of that attraction. I can measure the energy of that attraction using what is called Coulombs Law. Now, Coulombs Law here is the energy, talking about the energy of attraction between these 2 ions. K is a constant, so Coulomb's constant K is equal to 8.99 times 10 to the 9th, and the units on that are joules, meters per Coulomb squared, and Coulomb is a unit of charge. Q1 is charge 1. Q2 is the charge on ion 2. And R here is the, and I feel like this is kind of a misnomer, R here is for radius, but it's really the sum of the radii, the sum of the atomic radii, in this case the ionic radii, because when these things fit together, we visualize ions as spheres. So if, for example, I have, let's take lithium bromide. So lithium bromide has lithium ions, which we can think about as Li+, and then we have bromide ions, which we just talked about with our magnesium, right? So lithium is one of our alkali metals. It likes to lose that 1 valence electron, and then our bromide likes to gain it. Now there's an energy associated with that gain and loss, but there's also an energy and association between the attraction between 2 oppositely charged particles. So when we're visualizing this structure, and ionic compounds in general, lithium is tiny, so let's just kind of visualize it as a sphere here. My bromide is going to be larger. It's got a larger atomic radius. It also gained electrons, so electrons increase the volume of an atom, or of an ion in this particular case. So when I put these things together, they're going to max min and rearrange themselves so that these things all fit together. So I have kind of maybe a big guy here, and these guys, a big guy here, and these guys, big guy here, big guy here, right? And we have all of these, my dots here represent my nuclei. So that R is going to be the ionic radius of my bromide plus my ionic radius of my lithium. So this is your R that you're going to use for this. Now if you're a physicist, or if you've taken physics before, you'll note that this is a slightly different version of Coulomb's law than you may have learned in a physics class. They're both the same. They're both relating to the energy of this attraction. Usually you talk about point charges in physics, but since we're talking about atoms and ionic radii, then this R is slightly different. So then you can kind of plug and chug your way through, and you'd end up with a way to calculate this energy. So an important thing is that the fundamental charge, which is the charge on an electron, is 1.6 times 10 to the negative 19 coulombs. And so when you're thinking about ions, these Q's are going to be multiplying the number of the charge times this fundamental. And we can work another example in future videos.